We're going to continue our discussion on atomic structure and periodicity with sections 3 through 5 in chapter 2. In section 3, we're going to talk about continuous and line spectra and explain the significance of atoms displaying line spectra when excited. A continuous spectrum is where we see all the different colors of light in a given wavelength range. In other words, a rainbow. That is a continuous spectrum. We see all the colors of the rainbow: red, orange, yellow, green, blue, indigo, and violet. White light sources, what we consider white light, are made up of those colors. And when we pass that through a prism, it breaks that into its component wavelengths, and we see a continuous spectrum. It means there's no breaks in between. However, when we look at elemental spectra, like in this case we have a hydrogen gas discharge tube, which is essentially like what we see as neon lights. There is an electric source, a high voltage source, with wires leading into a tube filled with hydrogen gas, and there's no wire on the inside, so what's actually conducting the electricity is the gas itself. That's what they call the arc. Now, when we pass this through a prism, we do not get a continuous spectrum. We don't see all of the colors of visible light. Instead, we see what is called a discontinuous or a line spectrum. A discontinuous or a line spectrum will only show discrete wavelength bands. So we can see here 410, 434, 486, and 656 nanometers. So we'll get orange light, like an aqua light, a blue, and a purple light. Now this was very different than what we might expect. We might expect, if we're seeing light, that we'd see all the wavelengths of light, or at least all the ones that make up a certain color. But this discontinuous spectrum actually tells us quite a bit about the nature of the constituent atoms, in this case the hydrogen atoms. Using the concept of energy quantization and the wave-particle duality of Einstein, we can actually surmise that the reason we see different energies and different frequencies and different wavelengths within a discontinuous spectrum has to do with the nature of the electron. That electrons in excited energy states would give off light, so the electricity flowing into the discharge tube causes the electrons to be excited, and when they fall back down to some normal state, they must give off energy. And they do so in discrete packets. So here we have what is listed as delta E1, delta E2, and delta E3. Now, this change in energy is equal to hc over the wavelength of light produced. So that is the change in energy from this level back to the bottom level. Energy 2 would be from this level, circled the wrong level before, that level down to the same level, and energy 1 would be from that level down to the other. Now we can see that this is really kind of like a staircase, but the staircase in this case has a really, really big first step, and each of the subsequent steps gets closer and closer together. And we're going to see how this concept was used to construct a model of the atom. In section 4, we're going to talk about the Bohr model and explain why the Bohr model defied conventional physics. We'll also calculate the energy of the transition of the electrons between the allowed states within the Bohr model and explain why the Bohr model ultimately failed to predict energies of other atoms. Alright, so the Bohr model is probably the simplest model that we have seen. Oftentimes you see this in grade school when we talk about the nature of matter. And what we use is we use concentric circles to show states in which electrons can exist. Okay? Now, we've got these n levels. Okay, n equals 5, 4, 3, 2, 1, so on. These n's are what we consider allowed energy states. And the reason this is important is because Bohr said, okay, if electrons are circling the atom, then there's got to be a constant input of energy. That's what classical physics says. There's got to be a constant input of energy. Otherwise, the orbit would decay down and crash into the nucleus. But that obviously can't happen. We know that opposite charges are attracted to each other. So a negative charge and a positive charge on the electron, the positive charge on the nucleus, they would be attracted to each other. So why is it that the electrons sit on the outside of the atom? So Bohr said, well, this would only work if electrons existed in discrete energy states, these allowed energy states. And using the hydrogen line spectrum that we had looked at, he actually came up with a semi-quantitative model in which he came up with what we call the n value, which we're going to find out is called the principal quantum number. And these allowed energy states break with classical physics, because if we were to put a satellite in orbit, we would have to constantly add energy into the satellite for it to stay in orbit. Otherwise, it's going to inexorably fall toward the Earth. As gravity is pulling it towards the center of the Earth, it's going to fall and crash into the Earth. But if we keep adding energy, then it can stay up there almost indefinitely. Well, electrons, we can't add energy. There's not energy being added all the time. Therefore, these allowed energy states make sense. Now, we can also think of this in terms of de Broglie wavelengths. That the reason we can have these allowed energy states is that they must be multiples of the wavelengths of the electron in the energy level. So, for example, if I take a circle and I make my electron wave through the circle, if it fits perfectly like that, where it continues in the same standing wave, then it's an allowed state. But what if I had another electron, let's say a purple electron, that, say, started from the same thing but has a different wavelength? See how it crashes together at the same spot where it started? That electron wouldn't fit within the allowed energy state. Therefore, it couldn't exist in that state. So, it has to exist in a different energy state. And we can see that these concentric circles, each are going to have longer and longer, or bigger and bigger circles in which the electron waves could stand. Okay? Now, drawing concentric circles is kind of a pain, so oftentimes what we do is we sort of cut it into a single line, where n equals 1 is our bottom line. This is the ground state for hydrogen. Okay, for a hydrogen electron, n equals 1 is the ground state. Anything that's above there would be an excited state. And the change in energy is going to be given by the difference between the different quantum numbers, the different principal quantum numbers. And we can also see the movement between these states is related to the wavelengths that we see in the line spectrum of hydrogen. So Bohr actually came up with this model and came up with math to back it up. And that math is given here. The change in energy is the energy level of the final state minus the energy level of the initial. Does that sound familiar? Final minus initial, final minus initial. So energy final minus energy initial. Now this equals negative 2.178 times 10 to the minus 18th joules. This is a constant. Okay, this is actually known as the Rydberg, R-Y-D-B-E-R-G, Rydberg constant, times 1 squared over n final squared minus the Rydberg constant times 1 squared over n initial squared. Or we can collapse that down into a single equation. Delta E is equal to the negative 2.178 times 10 to the minus 18th joules times 1 over n final squared minus 1 over n initial squared. Now this is the equation that Bohr used to identify the wavelengths and the corresponding energies produced from the emission of light from the hydrogen atom. So let's use this equation and calculate some of the transitions within a hydrogen atom and talk about what type of wavelength or what type of electromagnetic radiation we're talking about. All right, let's do part A. For n equals 3 going to n equals 2, the change in energy, delta E, is equal to the negative 2.178 times 10 to the minus 18th joules times 1 over n final squared minus 1 over n initial squared, which is equal to negative 2.178 times 10 to the minus 18th joules times 1 over n final is 2, so 2 squared is 4, minus 1 over n initial is 9, so we have 3.025 times 10 to the minus 19th joules, negative. Now this is a negative because energy is being given off. Okay, so the change in energy is negative, energy is being released. The absolute change in energy would be the 3.025 times 10 to the minus 19th joules. Now what wavelength of light does this correspond to? So the energy is equal to hc over lambda, or lambda is equal to hc over E, which is equal to 6.626 times 10 to the minus 34 joule seconds times 3.00 times 10 to the 8th meters per second over the 3.025 times 10 to the minus 19th joules. I'm not putting the negative in because you can't have a negative wavelength, and we're looking at just the energy of that photon. And we see that lambda is equal to 6.57 times 10 to the minus 7th meters, or 657 nanometers. Now, 657 nanometers, this corresponds to red visible light. Let's do for C, n equals 2 to n equals 1. So delta E is equal to negative 2.178 times 10 to the negative 18th joules times 1 over n final squared minus 1 over n initial squared. And plugging in our values, we get negative 2.178 times 10 to the minus 18th joules times 1 over the final squared was 1 squared minus 1 over the n initial was 2 squared, or 1/4, and we get delta E is equal to a negative 1.63 times 10 to the minus 18th joules. And again, to determine the wavelength, E is equal to hc over lambda, or lambda is equal to hc over E, which is equal to 6.626 times 10 to the minus 34 joule seconds times 3.00 times 10 to the 8th meters per second, all over 1.63 times 10 to the minus 18th joules. And again, I'm dropping the negative sign because you can't have a negative wavelength. And we're talking about the absolute energy of the photon. And this is lambda equals 1.15 times 10 to the minus 7th meters, or 115 nanometers, which is in the ultraviolet portion of the spectrum, the UV. Now, unfortunately, the Bohr model was a semi-quantitative model, okay? He took a lot of known work at the time and applied it to the hydrogen spectrum and worked out the energy levels. And it worked for hydrogen, and hydrogen alone, because when there's more than one electron, we have electron-electron repulsion, and this changes the energies. And since the rest of the periodic table has more than one electron, you can see that there's a problem. Okay? Now, Bohr spent quite a bit of time trying to adjust his theory, changing the shapes of orbitals and all sorts of stuff, but he was never able to work it out because it's not like a static orbit of the electron around the nucleus. It's something way, way more complex and way weirder. So in section 5, we're going to talk about that weirdness, and we're going to talk about the development of wave mechanics by a guy named Erwin Schrödinger. We'll talk about the wave function. We'll describe the Heisenberg uncertainty principle, and we'll learn how to calculate uncertainties in position or in velocity using that principle. We'll talk a little bit about the uncertainty principle in terms of electron position, talk about the physical picture of the wave function and its probability distribution, and how the probability distribution corresponds to the term orbital. Okay, so we had talked about waves fitting within these orbits, these allowed energy states. Well, Erwin Schrödinger took that a little further. He developed a whole series of math called wave mechanics to try to explain the energy levels of all of the electrons. And he used the same concept that I had talked about previously, using de Broglie wavelength to sort of understand these orbits. Now, the interesting thing that he does is he describes this something called a wave function. This Greek letter psi, that is the wave function. Okay? And when you take a special operator, the Hamiltonian operator, I'm not going to get into this because it's way above what we need to know. But when we operate on that wave function, we can actually calculate the energy of the wave function. Okay? Scientists like this. Physicists loved wave mechanics because waves are easy to understand. Now, there is more information that pops out of the wave treatment of the electron. However, we have to sort of do some jumping around because at this time, everybody was muddling through physics. It was all just disarrayed, and none of these discoveries happened linearly. They were all sorts of just stuff jumbled together. So we're going to talk briefly about Heisenberg's uncertainty principle and how it affects the wave function. All right, Heisenberg, Werner Heisenberg, was a German physicist, a contemporary of Schrödinger, about 15 years younger. And that actually is kind of a whole interesting thing about physicists doing their best work before their age 25. Most physicists did their best work before age 25. Schrödinger was ancient. He was 34 when he developed wave mechanics. But Heisenberg was a young guy, and he was tackling the same problem as Schrödinger. Okay? And from the math, what he developed was an uncertainty principle. Now, the Heisenberg uncertainty principle is mathematically equal to the equation set forth here. This equation is hugely important. What this states is the uncertainty in position times the uncertainty in momentum Now, momentum is equal to mass times velocity. We've already sort of talked about that. The uncertainty in position times the uncertainty in momentum must be greater than or equal to h over 4 pi, where h is Planck's constant. All right, so what is this? This is saying that you can never know the precise position and the precise momentum of a particle. You can only know relative degrees. The more you tack down one aspect, say position, the less certain you are about its momentum. Okay? Now this is huge. I mean, this principle, I cannot overstress how important and just fundamentally important to all of physics. This has nothing to do with how good your measurements are, although there is something to that. It is an underlying principle that instead of having a deterministic universe, where if we know the position of everything, we can calculate out everything else. That was one of Einstein's things, is if he knew the position of everything, he could use his principles to calculate the universe. Well, we don't live in a certain universe. We live in an uncertain universe. This is actually a probability. Okay? It lends itself to a non-deterministic universe, a probabilistic universe. Okay? So, if you can tack down where the electron is, then you don't know how fast it's going. If you can tack down where the electron is, if you can tack down how fast the electron is going, you'll have no idea where it is. In other words, when we tack down how fast it's going, what we're really looking at is we're looking at energy, right? Because kinetic energy is equal to 1/2 mv squared. If we know the velocity, we know the energy, and we have the mass of the electron as a constant, well, now we don't know where the electron is, and that's a problem. Now, this fits into the wave function in that if you square the wave function in terms of position, x, y, and z coordinates, you square those, you get a probability density function. And what is a probability density function? It's essentially a map. And when we square the wave equation, we get this map of where the electron could be. But we can't know exactly because of the uncertainty principle. So what we get is this beautiful little picture of a fuzzball. What we can say, though, is within this fuzzball, we've got a 90% probability of finding an electron. 90% probability of finding an electron. Now, the probability increases the closer you get to the nucleus, and it decreases the farther you go from the nucleus. So this probability density function actually comes out to be hugely important. This is what we term the orbital. It is not an orbit, it is orbit-like, hence the term orbital. Orbitals are where electrons reside. Okay? And it's through the application of the wave function and Heisenberg's uncertainty principle that we can determine the orbitals. Now, there is a lot more to this than the simplistic treatment I am giving. There are a lot of things that you should read, and your book does not do the greatest job of talking about the interrelations of these things. But if you want to know more about how this all works out, it is a fascinating area of physics in the early 20th century. There's a lot of cool and very weird things that can happen that come from this concept. Now, this is the wave mechanics. What we term quantum mechanics is actually the combination of Heisenberg has not his uncertainty principle, but he actually came up with something called matrix mechanics. And when you put matrix mechanics and wave mechanics together, you kind of get what we term now quantum mechanics. The wave equation, as I said before, physicists love because understanding waves is easy. Matrix mechanics, the math is very, very difficult, and it was not liked by a lot of people. However, Heisenberg's approach, while mathematically very different, was actually vastly superior for a lot of different things. But here's the lovely thing. Chemists don't need those extra little bits that Heisenberg's matrix mechanics gives us, that we can understand wave mechanics, and we like it because we're really just caring about where the electron is and what it's doing. Okay? So, let's use Heisenberg's uncertainty principle to calculate the uncertainty and position for each of the following. As I said, this is a bedrock principle of all of science. The uncertainty principle is hugely important. So I want you to be able to calculate uncertainty in position and uncertainty in velocity. So, using the Heisenberg uncertainty principle, calculate the delta x for the following. So we have an electron with a delta v, an uncertainty in velocity of 0.100 meters per second. Okay? So remember, delta x dot delta mv must be greater than or equal to h over 4 pi. Alright, so since the electron, we know the mass of the electron, there's no uncertainty in the mass, it's really uncertainty in the velocity. I can rewrite this as delta x dot m delta v must be greater than or equal to h over 4 pi. And all I'm going to do is I'm going to solve for delta x. So this becomes delta x must be greater than or equal to h over 4 pi mv. Okay, and this is equal to 6.626 times 10 to the minus 34 joule seconds over 4 pi times the mass of the electron is a constant that you can look up, 9.11 times 10 to the minus 31 kilograms, times the uncertainty in velocity was given to us as 0.100 meters per second, and we get 5.79 times 10 to the minus 4th meters. Now that's pretty small, but when you consider that we're talking about the difference, this uncertainty in position, let's say this were something like a physical picture. The uncertainty in position would be something like, I know how fast I'm going within 0.1 meter per second, but I could be in the state of Iowa instead of the city of Rockford. This is a very large uncertainty in position. That electron could be pretty much literally anywhere else other than the atom in which it first started. Now let's do this with a baseball. Okay? Now, a baseball has a mass of 145 grams with a delta V is equal to the same 0.1 meter per second. So, delta x dot m delta V must be greater than or equal to h over 4 pi, or the uncertainty in x must be greater than or equal to h over 4 pi m delta V. And that's 6.626 times 10 to the minus 34 joule seconds over 4 pi times, now the mass has to be in kilograms, so 0.145 kilograms times 0.100 meters per second, and we get an uncertainty in position greater than 3.63, actually 3.64 times 10 to the minus 33 meters. Now remember, The uncertainty in that position must be greater than a very, very tiny number, which means essentially there is no uncertainty in this position. You see the baseball, you know how fast it's going, you know how much it weighs. That's all it is. But with the electron, the uncertainty in its position would be as if a pitcher pitched the ball in Wrigley Field and it disappeared from Wrigley Field and immediately reappeared in Antarctica flying through the air because the uncertainty in position is so large. So, obviously, the uncertainty principle does not work for macroscopic objects. We're pretty deterministic at the macroscopic scale. I see something, I know where it's at, I know how fast it's moving. But at the microscopic or submicroscopic scale, these uncertainty effects become hugely important. And lest you think that this is all just academic math tricks, this explains a lot of things that we see in engineering. For example, cell phones have become microscopic computers. Now we're hitting a limit to how good our computers can be because we're actually starting to lose electrons. If you leave your phone off, your battery will drain even though there's not been a load applied to it because those electrons moving through the battery actually we lose them. As we use computers and calculators and whatever, using these electrons throughout their circuits, they can start jumping circuits. We get what's known as a bleed current. It's really, really important. And it is a fundamental aspect of nature that we cannot get past.